Very good morning, my dear student friends. Yesterday, we were discussing about the control chart for variables. Okay. We discussed the difference and the similarities between control charts for variables and attributes. And then we also know that the control chart for attributes will be used as a cursory thing for maintaining inequality characteristics. And if that means cursory analysis can be done with the help of control chart for attributes, and the detailed analysis will be carried out by control charts for variables. And we also know that there are four types of control charts for attributes, namely P chart, NP chart, C chart, and U chart. And we were discussing something about the type 1 and type 2 errors, and wherein we stopped it. Okay. That means the type 1 error, we said, type 1 error, in reality the process is in control. Nothing is wrong with the process. Process is correct. Process is correct or universe is correct. Process is correct. But when we take the sample, that says that the process is out of control. Okay? From the sample, whatever we are going to conclude, that is, it says the process is out of control. That means we have determined the control limits, and when I take the sample average or the range, if it falls outside the control limit, then we conclude that the process is out of control. But in reality, it may not have. That means we know that when we fix 3 sigma limits, we know that about 99.73% of the values will fall within plus or minus 3 sigma limits, and only 0.27% will fall beyond the control limits. So when I take a sample of 5 or 10 or whatever it is, it may say that one might have fallen outside the control limit. Even if I had taken a sample of around 1,000, only 2 or 3 might have fallen outside the control limit. The same thing if it continues. So that is one likely error. That means type 1, that is called as type 1 error. The process is correct, but our conclusion is, by taking the sample, our conclusion is, it says that it is not correct. Process is not correct, or that is out of control. This is called as type 1 error. Next, type 2 error. In reality, the process is out of control. Process out of control. But the sample says that the process is in control. Which is called type 2 error. Hence, which one is to be considered, whether we will give more importance for type 1 error or type 2 error, we need to understand. Okay, type 1 error, even if we commit, we might be on positive side, because nothing has gone wrong, but we have concluded that it is out of control. Okay? For that purpose, we might have stopped and we might have carried out the investigation, and after carrying out the investigation, we come to know that nothing is wrong. So it may not be of that much seriousness. But second one, if you look at it, type 2 error, we think that everything is going all right by taking the sample, but the things have gone bad. That means the shift has taken place, we are unable to identify that. Okay? That is what is called as type 2 error. That means already it might have started manufacturing the defective parts. Later on we'll come to know. Okay? That means type 2 is more serious compared to type 1 error. and how to control these things. But that is why, because specifically I want to discuss about why they choose the 3 sigma limit. Why not sigma limit? Why not 2 sigma limit? Or why not 3 sigma limits? That in the previous class I might have just touched upon, but I am taking this opportunity to explain about it. Okay. So that means why they are considering 3 sigma control limit only. Well, we know that when we take the sample averages, always it will follow the normal distribution because of the central limit theorem. And this one is also, we also know that mu plus or minus 3 sigma mu plus or minus 2 sigma and mu plus or minus sigma limit. What is the area we know? For between this one 3 sigma limit, this it works out to be 99.73. Whereas between plus or minus 2 sigma limit, it will be something around 95.65. And mu plus or minus sigma, the area in the normal curve between those ranges, it is going to be something around 68.46%. Okay, that is what it means. So now if we talk about type 1 error, what is the probability of committing the type 1 error? Process is actually not changed, but it says that the process is out of control. If we take 3 sigma limits, then whatever is outside these control limits, they will constitute the error. That means 99.73% of the area is, it shows, it correctly it shows. Only 0.27% it is natural variation. So if I adopt 3 sigma control limit, committing of type 2 error is 1 minus 99.73%, or it is only 0.27%. I can commit that error. But if I had made it to mu plus or minus sigma limit, then 1 minus 68.46, that means something around 31 point odd percentage, around 31.5% of this thing I will be committing the type 1 error. Similarly, for sigma plus or minus 2, that is around roughly around 4.5% I will be committing the type 1 error. What about type 2 error? The area between the control limits, those are type 2 error. Okay. See, the question might be asked to find out what is the type 1 error. When you apply 3 sigma limits, this is what is going to be the error. If it is 2 sigma limit or whatever it is, because you are going to calculate sigma, and based on that one you can calculate that one, whatever is outside 3 sigma limit, it is type 1 error. Whatever inside the control limits I am talking about, okay, control limits, those will be the type 2 errors. What I am talking, the control limits, okay. That means in reality it is going to be the X double bar and the sigma bar or whatever it is, that is what sigma prime, we calculate, that sigma X bar, we calculate whatever it is, that is what is to be understood, okay. These are the control limits, that is why. This is type 1 or type 2 error, whatever we are going to do it. So that means type 2 error is how much? The area between the two limits. If we adopt for 3 sigma limits, then 99.73%, if the process has actually changed and it will not be detected, it will be that much. So that means the type 1 error and type 2 error, they will be opposing each other. If type 1 error, if I try to decrease the type 1 error, type 2 error increases. If I try to increase the type 1 error, then the type 2 error decreases. Hence, the happy situation, they concluded that 3 sigma limit is the best thing. Okay. Hence, 3 sigma limits are being considered. This is the theory behind the fixing up of 3 sigma limit. Is it followed? Okay, that is most important. Okay. Now, in yesterday class, that is what I had stopped at. So, I just repeated that one. Now, we'll see what are the control limits for P chart, NP chart, C chart, and U chart. First, let me think about that one. So, first I will discuss about that, and randomly we will select the problem. Then you should be able to identify whether which control charts for attribute is to be applied. That might be the better practice. So otherwise, what we can do, okay, one more thing is P chart, explain about P chart, then take up the example corresponding to that, and then explain about NP chart and take the corresponding example like that. But whatever the method I am going to follow is not that. I will explain about the theory behind this, and then randomly we will pick up the problem and see which the chart is to be, appropriate control chart is to be applied for that. Okay, now control limits for P chart. Already we know that in attribute this thing we can classify it as is it present or absent or defective, good items like that, only dichotomous in nature. That is what we discussed. Hence, most of the time binomial distribution is applicable for the P chart, the fraction defective. It might be fraction defective or it might be number of defectives. So, binomial distribution needs to be applied. If the binomial distribution is to be applied, then what is the mean of binomial distribution? We know that is equal to NP. Okay, if P itself is the average values, then it will become P bar. Okay. For this one, if it becomes P bars, then standard deviation, that is sigma, is given by under root NP bar Q bar. For this one. But when we talk about P chart, now we are getting NP bar. Okay. That means if I use 3 sigma limits, let me say for sake of argument, then the upper control limit, just I will mention, upper control limit will be is equal to, this one is, what is the mean value? Mean value is NP bar plus NP bar Q bar, 3 sigma limit into 3. Lower control and central line is NP bar. Lower control limit is NP bar minus 3 sigma, that is NP bar Q bar. What has happened? Now, if I look at it, it will give the number of, average number of defectives. NP bar is average number of defectives. Try to understand. These will become the control limits for NP chart, where number of defectives. But what we are talking about is P chart. It should have only fraction defective. It shouldn't have the number of defectives. Okay, ultimately what has happened? I have given the mentioned, or we have identified the upper, the control limits for NP chart. In fact, I can write this one as USCL NP, CL NP, and LCL NP. These are the limits. Is it followed? Then for P chart, what is to be done? P chart, it should have only average fraction defect. Is it not? How do I find out this one? How do I find out? P chart. From here, I can find out that. What is that? Upper control limit. For P chart, I want to find out central line and lower control limit for P chart. Now, if you observe here, if I divide it by n throughout, so it will become np bar divided by n, that means it is p bar, and the corresponding things will remain. It is as simple as that. Is it understood? Then if I divide it by n, then I am going to get upper control limit. The upper control limit is np bar divided by n, so n, it gets cancelled. So I will be left with only p bar. Plus, observe carefully here, 3 under root npq, np bar q bar divided by n. Or if I take it under the square root, it is going to be divided by n square. So this one, it gets cancelled. So we are left with p bar plus 3 under root p bar q bar divided by n under this one, because of this reason, because I am going to divide it by n. That is the reason for this one. Similarly, this central line is going to be p bar and lower control limit is going to be p bar minus p bar q bar divided by n, square root of p bar q bar n. Is it understood? These are going to be the control limits. Okay. Now the question is when to use P chart and when to use NP chart. And already we have discussed that. In fact, there are 4 types of control charts for attributes. 2 are meant for when the fraction defectives or the number of defectives are mentioned. And 2 charts, namely C chart and U chart, will be used for when the defects are mentioned. So defectives, it might be given in the form of fraction defective or the number of defectives. So these are the control limits for P chart and the NP chart. Is it understood? Okay. Now, which one is to be used when? Try to observe carefully, and I also mentioned that in lieu of NP chart, always you can use P chart. But in lieu of P chart, you cannot use NP chart. So, we'll try to think why. Why that one? Okay, for example, whatever the sample I am going to take, it will go on varying. What this one? It is not necessary, because production rate, sometimes it increases, sometimes it decreases, and if I am going to do it, the number of samples, if it is the fraction or the percentage of the actual item produced. For example, I am going to take some 20% of the samples which are produced as the sample, total product. For a shift. In one shift, it might be producing 1,000 items, in the next shift, it might be producing 1,500 items. And 20%. So it will go on varying. That 1,000 means it is 200, but when it is producing 1,500, that means it is going to be 300. So that means the sample size, it varies. Yeah, it is most likely. Or it might be fixed. Okay? Suppose if it varies, what is going to happen? If it varies, that means sample size. For one shift, it is different. Okay? For the another shift, it is going to be different. Try to understand. n, because it involves the value n. That means even the central line will vary. For each of the sample, there is a separate central line you have to find out, separate upper control limit and the lower control limit. Can you envisage this one? If you compare with control chart for variables, we said there is going to be only three lines, straight lines. One is central line, another one is upper control limit and the lower control limit. Okay. If I adopt here, what is going to happen? The sample size, it will go on varying here. That means what the central line itself, it will go on varying because sample size will, the central line here, NP bar, means it depends upon the sample size. So for each this thing, it will central line, for one of the samples, it might be like this. It will go on varying. And again, the upper control limit and the lower control limit, they also depend on the sample size. They will also go on varying. So for each of the samples, I need to find out, in that case, the upper control limit and the lower control limit separately. Try to understand. This is for first sample. That means first sample, these are the control limits. Second sample, these are the control limits. Likewise, it will go on varying. Okay. But if the sample size is fixed, what is going to happen? Every time we are going to take only 200 samples or 300 samples. Then all the three will be fixed. Or especially these things, they will not very much about these things. They will be fixed. This is the advantage. That means we'll go for NP chart when the sample size is fixed from one sample to another sample. So the upper control limit, lower control limit, upper control limit, lower control limit, and central lines will be fixed. Just this is one straight line. These are the dashed lines, just like the previous one. One more thing you can observe, if this part is more than this part, NP bar, 3 under root NP bar, Q bar is more than this, then we are going to get here negative value. What is getting negative defective? It doesn't mean anything. In that case, we consider that it is 0. If it works out to be negative lower control limit, we will make it as 0. Otherwise, it doesn't give any meaning. Okay, that means what? NP chart is to be used when the defectives are given and a constant sample size is there. Okay? This is when we have to use NP chart. Now, we will just see the advantage of P chart. P chart here, it can be used when the sample size is fixed, same, or it is different. It doesn't make any difference for right. Whatever. Because anyway, the upper control limit and the lower control limit, they will go on varying depending upon the sample size. Because it involves the term n. But central line, it never involves the term n, unlike the NP chart. So for P chart, if I want to plot, the central line is fixed. It is at P bar. But upper control limit and the lower control limits, they are the functions of n. Not only P bar, but they will be functions of n. So for each sample, we will have to find out different control limits. But the central line, it remains fixed. That is the advantage of this P chart. This is how, because for each sample, I need to find out the fraction defective. That means upper control limit and lower control limits are to be found out. And then it needs to be compared. Okay? So P chart is the universal chart which can be applied whether the sample size, it varies from sample to sample or it remains fixed. Or if it remains fixed, either you can use NP chart or even you can use P chart. Okay, in that case, this will be fixed. And you will be drawing the same conclusion either from P chart or NP chart. Got this one? So you need to decide based on the sample size. We'll take up some examples and which will make the things more clear. Okay. Next, we'll try to understand what is C chart and when it is to be gone for. That is what we need to think. Now we said when the number of defects they are to be calculated. Okay, number of defects. This is the one. It has got several defects. Only one piece or number of pieces, but they are similar pieces. Their area of opportunity, because I cannot compare this one with the another different type of defect. No, it has to be same area of opportunity has to be there. But the occurrence of these defects might be less. That is what we say that rare events. That is why for rare events, which type of distribution is used? Yes, Poisson distribution is used. That is what we said when P tends to 0 and N tends to infinity, but the product of NP, there will be one finite value, say around 15 or 20 or 25. Yes. And everything tends to be normal afterwards. Okay. So this is the crux. That means P is less, or the fraction defective instead of fraction defectives, we are talking about the number of defects. That means virtually 1 unit we might be able to compare, or a big casting. I want to see. What are the normal things? Normally we expect so many cracks or the blowholes or blemishes or whatever it is, like that. Okay? In those cases, this is what the defects need to be compared. And then we are going to use the C chart. And U chart, when we are going to use this area of opportunity, it varies. To make it clear, this is the desk, okay? This area is different, and that is also another desk, its area is different. Okay? By square meter or some square foot or whatever it is, area, per area I can compare, not as a whole. No. Is it no? Because we have to give the fair opportunity. Say that is what I was mentioning yesterday, the cloth. It might be produced in length of maybe around 3 meters, 2 meters, 4 meters, like that. Whether they are every time they are going to record every meter length. That means inspection this one. Somebody has to inspect it. No? That is why. Or sometimes they may inspect every 2 meters. One center like that, one more this thing center like that. Then it differs. Still, you are going to count the number of defects only. So, under these circumstances, if the area of opportunity is fixed, or the number of units every time you are going to test, they are going to be fixed, and you are going to count the number of defects on average per unit, then C chart is used. And as already I told you, it is a rare event and it follows the Poisson distribution. So what is the characteristics of Poisson distribution? Poisson distribution is its mean of Poisson distribution is given by C prime or C bar, or it is also NP, number of this thing, defect, this thing, this is what I can do it. Or we call it as lambda also. Standard deviation, it is square root of C prime, or it is also square root of NP, or it is also square root of lambda. That means variance and the mean of the distributions are same, then variance, mind it, no standard deviation is square root of variance. Then we are going to use the Poisson, it says Poisson distribution, so here Poisson distribution will be used. So control limits, the same thing. Center line is how much? C bar. Upper control limit, C bar plus 3 times the standard deviation, because everywhere it is same. Lower control limit, C bar minus square root of C. Simple. This is the thing. Everywhere it is center line and 3 times the standard deviation. That is the common thing for any control chart. No difference. But only thing is, which one should be the central line? That means mean. It corresponds to what? And standard deviation. What is that value? That is what you need to calculate. That's all, as simple as that. Next one is U chart. That is what I told you. It is almost similar to C chart, but area of opportunity, it differs. It might be similar to P chart. U chart is similar to P chart. And C chart is similar to NP chart. That means if the sample size is fixed, then you are going to use C chart. If the sample size, the opportunity of area of this one, it varies, then we are going to use U chart. And correspondingly, we can find out the control limits for U chart. Central line for U chart, it is U bar. Upper control limit for U chart is equal to U bar plus 3 times U bar by N, where N is the sample size. Similarly, okay, these are the control limits. So our things will move around these things only. Okay, is it understood? Now, if it is understood, then we will take up the problems and go ahead with that. Okay, take down this particular problem. So I'll start with some simple, basically, and then we'll see some complex type of problems. Okay, following are the inspection results of magnets for 19 observations. Okay. Okay. Now, what are the things given? Some 19 observations. So those he mentions it as weak number. Weak number 1, likewise. Second one, number of magnets inspected. Inspected. Third one is number of defective magnets. See, sometimes what happens, the problem statement might be more. The answer will be very small. Number of steps required to reach the answer solution is very less. Yes, what I will do, okay. Week number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. 19 weeks. First week, number of magnets inspected. Seven 24, 763, 748, 748, 724, 727, 726, 719, 756, 719, after that 759, 745, 736, 739, 723, 748, 770, 756, 719, 757, 760. Okay. These are the samples taken. Now, number of defective magnets out of these samples of 724, 48 were defective. Out of 763, 83, 70 like that, 85, 45, 56, 48, 67, 37, 52, 47, 50, 47, 57, 51, 71, 53, 34, and 29. Okay? These are the things given. What he wants us to find out. Calculate the average fraction defective. Calculate the average fraction defective and 3 sigma control limits. Okay? Comma. Construct the control chart and state whether the process is in statistical control. Okay? No other things have been asked now, because it will tell us what are the things to be done. And he has given the straightforward problem, because what he has said, calculate the average fraction defective and 3 sigma control limits. What does it mean? Average fraction defective means P bar you have to find out. That means we need not have to bother much about it. If you had said, construct the appropriate control chart, then it would have been the better thing. Why I say then we have to think which chart is to be used. Because sometimes we may think that whether we can use C chart. Try to understand here. But here, the word what he has used is number of defectives. So that it should rule out, we cannot use C chart or U chart. Because those are concerned with defects. He is using defective means either it has to be P chart or NP chart. Now which one is to be decided now? Either P or NP chart? Which one? Appropriate? Because then we look for the sample size. The sample size, it is varying. Sometimes it is 724, 763, 759, so much variation. It is going to 770, like that. It will go on varying from 736, for example, 736 or 723. 723 to 719 to 770, it varies. This is what is happening in this case. Okay? That means we cannot use NP chart. If all were 700 or something like that, okay, fine. Then we could have used. Okay? But since they are varying, we cannot use NP chart. It has to be P chart. Again, in addition to that one, what he says, well, that is what he says. That means we need to find out the upper control limit and the lower control limit for each of these observations. Try to understand. For each of these observations, what I should find out? Upper control limit, central line, and a lower control limit. Try to understand. Okay? Because already we have identified the equations. That means P chart is to be used, means upper control limit of P chart is going to be P bar plus 3 under root P bar Q bar divided by M. Central line P bar. Lower control limit P bar minus 3 square root of P bar Q bar divided by M. So in any case, I need to find out P bar, hence I can find out Q bar, the other things can be worked out. Now let us see, how do I find out the P bar? How do I find out the P bar? How to find out? Things are very easy. Total number of defectives divided by the number of pieces irrespective. That means this one 48 plus 83 plus 70 like that up to 29 divided by 724 plus 763, 7 this thing like that. Is it understood? So that means that value is how much it works out to be. This will work out to be 14,14091. This works out to be 14,091 091, 14091. Okay, 14,091, and number of defective magnets, whatever are there, that works out to be 1030. You got this one? So average fraction defective will be how much? Average fraction defective is going to be P bar is equal to 14091 divided by 1030. This will work out to be the fraction defective. It works out to be 0.0731. So that is how we are going to calculate P bar for this one. But there is other way around also, calculating this. How? What is the other way out? Now P1, P2, P3 like P19 we can find out. P1 is equal to how much? 48 divided by 724. P2 is how much? 83 divided by 763. Because nevertheless it needs to be found out. No way out for us. Because if we want to compare, I need to find out the fraction defective. For fraction defective for each of these samples, it has to be found out. So that is why I am telling you the other way around. Okay, P bar, how we can find out. So let us do that one. So here we'll find out, before doing all these things, what is the fraction defective. We can calculate. Okay, that means fraction defective for this one is 48 divided by 724. That is going to be 0.066. 0.066. I should have taken this one bit apart. Okay, however, I need to manage with this. Second one is 83 by 763. That is 0.109. 0.1109. The third one is 0.094. 0.11. I'll just start with 0.114. 0.062. So I'll write only three numbers. The things are understood. Point 077, 066, 093, 049, 070, 064, 068, 065, 076, 066, 094, 074, 045, and 038. What this one? So other way is, what I could have done, I would have summed up all these things, is all point, and divided by 19, I would have got the same results, P bar over. What this one? The next, because I need to hurry up now. The next one, what we will do is, these are the things which have been calculated. Now I have to calculate upper control limit and the lower control limit. So now the decision is to be taken whether for each sample size it is going to be divided by n, or whether we can find out some average sample size. And it is recommended that if the variations are within 5 or 10%, then it is better to go for average sample size. So average sample size here it will be 724 or whatever it is, that is 14,091 divided by 19, 742. That is, it approximately works out to be 741.63. Let us say it is 742. So now we can find out the upper control limit and the lower control limit by substituting that this one is sample size n is equal to 742. That is what we are trying to do. Okay. Then it becomes easier. Almost it is going to be fixed. It will not vary now. Almost it will behave like NP chart. No other way out. Okay. So that means upper control limit we can calculate by substituting the value of P bar and n is equal to 742. Upper control limit, it works out to be 0.1018. I am very fast now. 0.1018, and this is 0.0731, and lower control limit 0.108, and this will become more, so it is going to be negative value, hence I consider it to be 0. Okay. Now we will compare this one. It has to go, these values whatever are there, it should not be more than 0.1018. Any value is more than that, 0.1018. That is what? The various values are there. So hence, if we look at it, second and fourth, if we look at it, second and fourth. So upper control limit, lower control limit, no, so sorry for that. The lower control limit is 0.0444, not 0. 0.0444. Okay. Now, which will cross this one? Second and the fourth, they are more than the upper control limit, namely 0.1018. So, this is out of control. The another thing, if you observe 19th, it is 0.038. It should not be lesser than 0.04444. That means the process is better. But still we need to find out the cause for that. Okay. For this point of time, I will be stopping because the time is already up. So in subsequent class, I will just take up this one and we will go to some other problem. Okay. Thank you.